Welcome to module number 1, where we're going to begin discussing the logic of atomic sentences. So remember back in module 0, we talked about first-order languages and how we construct atomic sentences. And now we'll be saying a bit about some of the logic of atomic sentences. Okay, so in this module, we've got 5 sort of main learning objectives that sort of go in order here. The first is to be able to identify the premises and conclusion of an argument. So we'll give the definition of what we mean by an argument and give a bit of vocabulary. Then we'll classify our arguments into arguments which are valid and arguments that are invalid. And we'll talk a bit about how you prove something is valid. That's with some sort of formal proof or something along those lines. And how you show something is invalid, that'll be by constructing what we call a counterexample. Now, in addition to validity, we're also going to be interested in whether or not our argument is sound or unsound. And soundness has to do with whether or not the premises are actually true or false. So you need some sort of world or some place to interpret the atomic sentences and determine if they're true or false. To determine if an argument is either sound or unsound. Whereas for valid and invalid, that's not necessarily the case. Okay, so once we get through those two things, valid and soundness, we will move into talking a bit about counterexamples. And pretty much along the way, we'll start introducing and talking about the system F, or the Fitch system, which is going to be our method for writing down and stylizing formal proofs in our deductive system. So we'll say a bit more about that. And we'll also be introducing more about Fitch as the semester goes on and as we go through more modules. So this will just be sort of an introduction to the syntax and sort of the basics of what Fitch is. Okay, so on this slide, we'd like to introduce the definition of what we mean by an argument. So at the most fundamental level, an argument is just a series of statements, and those statements can be sentences in a first-order language, or maybe just sentences in English or some other language, but they're just a series of statements in which one is a distinguished statement called the conclusion, and that conclusion is meant to be a consequence of the other statements, and those other statements are called the premises of the argument. So there's one conclusion, and it's sort of standing out, and then everything else is a premise. And a good example of that is right here on the left. You can see a sequence of statements in the block language. The first atomic sentence is right of BC. So in other words, if we're sort of translating that back into English, B is to the right of C. The second statement in this series of statements is left of DE, which means that D is left of E. The third sentence, atomic sentence in this case, is that B is identical to D. In other words, B is equal to D. And then the final statement here is left of CE. In English, C is to the left of E. And remember here, because we're dealing with the blocks language, B, C, D, and E all are terms for some blocks on sort of checkerboard grid, like you might see in Tarski's world. And the bar on the left sort of keeps the sequence of statements together, telling you which is the first and the second and the third and so on and so forth. And you can have as many statements as you'd like in an argument. And then that tiny little horizontal bar there before the last statement, left of CE, tells you which of the statements is a conclusion. And remember, it's meant to be a consequence of the others, but it doesn't necessarily have to be. So if we're just looking at sort of the formal definition here of an argument, it's just a series of statements in some language where one of the statements is distinguished, it's called the conclusion, and everything else is called a premise. Okay, so we have some really nice notation here for arguments, and it's the idea of being valid. And an argument is said to be valid if the conclusion of the argument must be true in any circumstance in which all the premises are also true. Okay, so if each one of those premises are true, then you can be certain that the conclusion has to be true as well. And when this situation occurs, we say that the consequence is the conclusion is a logical consequence of the premises. In terms of validity, we'll be interested in one of two different things: either verifying that an argument is actually valid, or somehow showing that an argument is invalid. So to show that an argument is valid, we use a method called a proof. And a proof is a step-by-step demonstration that a conclusion, let's say S, for example, follows from some premises, say P, Q, and R. And there can be more or less than just P, Q, and R in those premises. And the way that a proof works is by establishing a series of intermediate conclusions, each of which is an obvious consequence of the original premises and the intermediate conclusions previously established in the proof. And by obvious consequence here, we mean something like a logical rule or a method of proof. And we'll be introducing several different types of methods of proof and being a little more clear about what an obvious consequence means. The proof ends when we finally establish the conclusion S as an obvious consequence of the original premises and these intermediate conclusion steps. And there are going to be two types of proofs. There are formal proofs and informal proofs. Informal proofs are just written in everyday sort of English language, and they're not imprecise. They're very precise sort of mathematical objects. But what we mean by informal is just that they're written in everyday English. On the other hand, formal proofs carry the same sort of information, but they're highly stylized, and the obvious consequences are laid out step by step. And so it makes it a bit easier to sort of work with them and write programs that can check whether or not they're actually a proof. Okay, so as a first example, let's go back and look at the argument that involved the block language. And here, what you're seeing on my screen is the fish program. So we'll do a bit of a mix of a formal and an informal proof. So it won't be a formal proof because I won't sort of include all the justifications, but we'll sort of walk through it sort of step by step and give the details of why each of the intermediate steps follows from either the premises or previous steps. Okay, so in our argument, we had something like the following right of BC. So that was one of our sort of assumptions there. And if you come up here to the top and you say, okay, we can add an extra premise. Our other premise was that left of DE. Okay, and then again, come up here to proof. We can add ourselves a premise. And the third premise that we had was B is equal to D. And again, these are three atomic sentences in that blocks language that we were investigating with Tarski's world. Okay, so now we can hit sort of this plus bar here, and you'll notice that we include this sort of horizontal bar And now we're working with the consequences of our premises. And what we'd like to do is write down a sequence of sort of consequences here that are sort of consequences because it's just obvious, right? So there's like a rule of logic, or there's a reason why we can believe they're an obvious consequence of the various premises. And then later on, we'll come back and we'll justify them and look at it as an actual formal proof. But for the moment, let's start by just reminding everybody that at least in Tarski's world and in the block language, the right of predicate and the left of predicate are inverses of one another. So for example here, this right of, we can take that and we can conclude that left of CB is true. Because if B is to the right of C, then C is to the left of B. And we say that right of and left of are inverse relations or inverse sort of predicates. Okay, so that would be the reason why that would be true. Okay, and then we'll add another step here. And in this second step, what I'll do is go through and replace D with B. And the reason I'll be able to replace D with B is that D is equal to B. They name the exact same sort of object. So because D is equal to B and left of DE is true, we can conclude left of BE is true. Okay. So again, we have another intermediate consequence here that is obviously true. And in this case, it's obviously true from the way in which equality works and the fact that we're already assuming left of DE. Okay, and then finally, we can make our final sort of conclusion here. And that conclusion is that we have left of CE. And the reason we can conclude left of CE is that the left of relation is what's called transitive. So if C is to the left of B and B is to the left of E, we can conclude that C must be to the left of E, and that's because left of is a transitive relation. Okay, and so you'll notice what we have here. We essentially have what amounts to an argument. It's a sequence of sort of sentences and then a conclusion at the end, with sort of the difference here being that we've now introduced some intermediate consequences. And those intermediate consequences we've justified either by the premises or previous sort of steps. And so this would be an example of sort of a mix of an informal proof and a formal proof, sort of formal here because we're starting to use the Fitch style system to write out our proof, but informal in the sense that I haven't sort of justified the rules and I haven't come up here and checked to see whether or not this is an actual correct proof. Nonetheless, the proof tells us that the argument that we were initially interested in is valid. And that's because if these premises are true above that sort of horizontal bar there, then each one of the intermediate consequences has to be true. And in particular, the final conclusion would have to be true as well. In addition to validity, we're also interested in whether or not an argument is sound. And soundness sort of extends the idea of validity. And we say that an argument is sound if it's, first off, an actual valid argument, right? So the conclusion is true anytime the premises are true. And furthermore, all of the premises are actually true, right? Because it's not always going to be the case that what we've listed in those premises are necessarily true. But if they're all true and the argument is valid, then we say that the argument is sound. And sound arguments have the feature that the conclusion is true, right? So we can rest assured that the conclusion is true. Be careful here. Whether or not an argument is sound really depends on the context and whether or not our various atomic sentences are either true or false. And as we've seen with Tarski's world, that can really depend upon sort of the picture and what's going on. So let me give you an example here on our next slide of our previous argument in the blocks language in such a way that the argument is both sound and unsound, right? So I'll give you a world where all the premises are true and a world where maybe some of the premises are false. Okay, so here we're going to be looking at the soundness of the argument we gave earlier in the blocks language. And I've included it here for convenience on the right. Those first three sentences are the premises, and the conclusion, that fourth one is left of CE. And we gave proof previously that this particular argument was valid. In other words, that fourth sentence was a logical consequence of the three premises above. And now we would like to determine if the argument is sound or unsound, and it really depends on whether or not the premises are true or false. And so therefore, it's going to depend on the world that we construct and how those blocks that we put into this world are related to one another. So let's see an example where the argument is sound and also an example where the argument is unsound. Okay, so first off, let's throw in just three blocks here into Tarski's world. Let me label this first one here a C, the middle one B and D, so it has two names. And then finally, this last one I'm going to name E. And let's just go through and evaluate these sentences. And we see that in this case, this configuration makes all three of the premises true. So indeed, B is identical to D. That's because they have the same name here. That's that one in the middle. B is to the right of C, and D is to the left of E. So all three of the premises are true. And because our proof was correct earlier, it's the case that the conclusion has to be true as well. And in this case, C is to the left of E. On the other hand, if we were to take this block that's named C and rearrange it, for example, maybe putting it over here, and then trying to evaluate this again, you'll now notice that the first premise is false because B is no longer to the right of C. In fact, in this case, C is to the right of B. So that first premise is false, and you'll notice that the conclusion here is false as well, even though we have a valid argument. In this case, it would be unsound. So be a bit careful here. The soundness of the argument depends on whether or not these sentences that you write down are true or false, and we can give examples of worlds here in Tarski's world where the statements where the premises are all true, and some where the premises, some of them are false, right? So really depending on the configuration of the world tells you whether or not your argument is sound or unsound. So now that we've talked about validity and soundness of arguments, I'd like to get a bit more into formal proofs, and in particular, what it means for something to be an obvious consequence. And throughout the semester, we'll be adding on more and more rules that allow us to go step by step in our proofs, making obvious sort of conclusions. But here we'll be specifically talking about proofs that involve the identity predicate. And the reason we can do this so early on is that the identity predicate is always interpreted the same way. It means that whatever's on the left side of that equal sign and the right side of that equal sign essentially names the same object in the world that we're trying to describe. And there are two rules associated to using the equality predicate in proofs. The first is equality elimination, which is denoted by this equal and then an elim. And what that says is that if B is equal to C, so if somewhere in your proof you already know that you have the statement B is equal to C, then whatever holds of B, whatever predicates or relationships that hold of B also have to be true of C. This is also known as the indiscernibility of identicals. And what it means is that if we have a sentence that, for example, has a B in it somewhere, then we can cite this B equals C in this rule, equality elimination, and replace that B with C and get a new sentence that no longer has B in it but has C, and we can be assured that it's true. Okay, so we can sort of replace identical objects. And we call this equality elimination because what happens in the proof is you go from a line where you had B is equal to C down to a line, an intermediate conclusion that no longer has an equality sign in it. And so in some sense, you've eliminated an equality symbol as you moved down your proof. There's also a way of introducing equality symbols into proofs. And that's what our second rule tells us. And really, it says that in first order logic, you're always free to assume that a term is identical to itself. In other words, if you have two terms, not two terms, but a single term B, then you can always be assured that B is equal to B. This is sometimes called the reflexivity of identity. And what it allows us to do is introduce an equality symbol into our proof. And it turns out that all of our rules will be sort of in this format. We'll introduce a new logical sort of symbol like conjunction or disjunction or negation sort of later on. And when we do that, we'll always have a way of eliminating that symbols from our proof and a way of introducing those symbols in our proof. Here on the next slide, I'm going to go through a proof of the symmetry of identity. That's this third bullet down here. So if B is equal to C, then C is equal to B. And the transitivity of identity. So if A is equal to B and B is equal to C, you can conclude that A is equal to C. In other words, those are valid arguments. And it turns out that they follow from these first two rules about proving things with identity. So we'll give a sort of formal proof of those two facts. But the point is just that, the underlying sort of features of identity are 1 and 2, right? That you can sort of substitute two things that are identical. And if you have sort of something that names something, it's identical to itself. Okay. And then those two things together get you, the symmetry of identity and the transitivity of identity. So let's give the proofs of symmetry and transitivity using equality introduction and equality elimination. Okay, so we'll be going through, and this will be our first example of a formal proof, even though I haven't sort of specified exactly the details of formal proofs, but here we'll actually justify why every step is an obvious consequence. So this will be a formal proof. Let's start with symmetry. With symmetry, the premise that we have is that A is equal to B. And the goal that we would like to obtain is that B is equal to A. Right? So that's what symmetry would say, is that if we assume that A is equal to B, then we can conclude down here that B is equal to A as well. Okay, and this isn't obvious. We're going to have to go through and prove it from equality introduction and elimination. So we're assuming that those two rules are obvious. and we'll use that to get down to this goal. Okay, so let me go ahead and add in a step in my proof here. And there's a few things to notice. There's an arrow here on the left-hand side telling us that we're sort of highlighting this particular step. Here we can put in a sentence in our first order language, and then over here we'll reference some rule. Why is this particular intermediate step an obvious consequence? And there's lots of different rules that we're going to sort of be related to the various types of symbols that we introduce and logical symbols that we introduced sort of later in the semester. But typically there'll be some introduction rule and some elimination rule. And we'll be talking again about equality, introduction, and equality elimination, right? So equality introduction just says that you can always assume things like, A is equal to A. And then equality elimination tells you can make sort of substitutions based off of equalities that you already know. Okay, so here, let me start off by just using equality introduction, just so you can see what the format looks like, and it's part of the proof as well. So here, I'll first write down A is equal to A, and the justification for that will just be equality introduction. And again, that's true for any term that I can come up with, complex term or anything like that in my language. I can always am free to assume that it's identical to itself. And so the rule I would cite here is this one. And you can check to see if that particular step is correct by clicking up here, and it'll give you a little check mark that says, oh, okay, indeed, this follows from the previous work. Now, be a bit careful. It doesn't really depend on the fact that A is equal to B up here. And our intermediate steps don't have to depend on each one of the premises at each stage. So here, this would independent of whether or not A is equal to B. Okay, so but now let's use that fact that A is equal to B, and we'll just make our actual conclusion. So at this point, we can actually get the conclusion that B is equal to A. In this case, we'll use equality elimination. And what equality elimination says is, you can sort of see it in this little slide here. If you have some sort of statement about n that's true, and you know somewhere that n is equal to m, well, then you can replace every instance of n with an m and sort of be assured that that's true as well. So let's do that with our previous two sentences. I'm first going to cite this sentence, and you'll notice that I come up and I click on it, and it turns red. And that means that I'm using it with this equality elimination rule. So to use equality elimination, you have to have some sentence P of n, and this is going to be that P of n sentence. And then I'm also going to cite this sentence up here that says A is equal to B. And what this tells me is that anytime that I see an A somewhere, I'm free to replace that A with a B. Okay, and that's because of the identicals can't be distinguished, right? Okay, and then I can hit verify whether or not this is true, and it'll give me a little check mark here as well. And again, the idea is that I took this sentence here, A is equal to A, which I knew was true, and then I used the substitution that anytime, because A is equal to B, anytime I see an A, I can replace it with B, and I replaced that first A over here with B, and I got my conclusion here. And then I can check the entire proof, and you'll notice that it gives me a nice check mark down here for my goal. So this is a formal proof that symmetry holds in our system, and it's using the equality introduction and equality elimination as the sort of basic rules or the obvious consequences in the proof. Okay, and that'll be part of all of our sort of languages that we introduce throughout the semester, because equality is part of every language. Okay, so let's now go back. Let's change our goal here. So again, notice you have to sort of click on the side here to get access to a given line. So like if I wanted to come back up to this line, that's the line that I'm now focusing on. But let's come down back over here to the goal, and let's say our goal now is that A is equal to C. And here, let's add in an extra premise. So I'm going to come up here and say, okay, let's add a premise, and we'll say B is equal to C. Okay, and this is the sort of argument for transitivity. So assume A is equal to B, assume B is equal to C. Those are our two premises. And if those two things are true, then we should be able to conclude that A is equal to C. And we'd like a formal proof here so that we know that that argument is valid. And we'll often refer to that as the transitivity of equality. Again, the formal proof that we would like to construct here is one that just relies on equality introduction and equality elimination. Okay, so it turns out that it's just a one-step rule, right? So I can basically immediately conclude that A is equal to C, and I can do that with equality elimination. So I have to cite some sentences when I use equality elimination here. And the two sentences that I'll cite are the premises. And basically, the idea here is that because I know B is equal to C, anytime I have a sentence that I know is true, I can replace any instances of B with C. And so what I did is, basically this sentence up here, A equals B. If I replace this B with C, I get A is equal to C. And then we can sort of check our proof here. And it tells us, yeah, that's correct. So this is an example of a valid argument. Okay, so we just saw a couple of good formal proofs. Now let's be a bit more detailed about exactly what we mean by a formal proof in our particular system, which we'll refer to as Fitch. So it's also the name of the program that we've been using to construct those formal proofs. But the system itself is also called Fitch. It's one of many different deductive systems, and so first-order logic has lots of them. The format that you're seeing here by sort of writing the sentences sort of vertically and using that vertical bar, and then later on we'll also introduce the idea of a subproof, was due to Fitch, and so we call this a Fitch style system. And there really are lots of different types of systems, but this is a good focus for our book because it turns out that each one of the justifications that we introduce will be related to sort of a method of proof that you might use in sort of a mathematics course. And so that'll be a nice sort of setup. But there are some systems that are very minimal in terms of their justifications and only allow for one type of justification, in which case there are a lot more sort of details about setup and things like that that you'll have to use. Okay, so the format is basically what you're seeing here on the left-hand side. We first use a vertical bar to indicate the sequence of sentences basically in our argument. So a proof is essentially a special form of an argument. So it's a sequence of sentences. And that very last sentence is intended to be the conclusion of the proof. Now, it's a little bit different than an argument has a bit more. There are intermediate consequences, and that's what the S1 through Sn are. And each one of those intermediate consequences is supposed to be an obvious consequence of either the premises, in this case P, Q, and R, or one of the previous intermediate steps that you've already identified as true. And again, here, it just has P, Q, and R as premises, but there can be many more, or just maybe one premise in this particular setup for a proof. In fact, you can even have a proof without any premises at all. Nonetheless, we still have this sequence S1 through Sn of intermediate steps. And the thing that makes it sort of the formal proof is that adjacent to each one of those, you have a justification. And typically that justification will go by citing some sort of rule, and you'll have to cite some previous sentences along this list. Now, you won't have to cite all of them because often it'll be an immediate consequence of only some handful of sentences on that particular list, but you'll apply the justification You'll cite exactly which sentences are involved in that particular justification, and you'll move on step by step until you get down to basically the goal that you're after. And that will be a proof that your initial argument is valid. In other words, if the premises are true, then the conclusion that you were trying to make with the proof happens to be true as well. And we've already seen a couple of really good examples of that sort of setup. But what I would like to do is come back to our sort of informal proof that I was starting to put into Fitch of the argument in the blocks world. And I'd like to go through and actually include the justifications in this instance. And it'll be interesting because it'll be our first instance of looking at something called analytic consequence, which is actually a feature of the program that we're using to construct these Fitch-style proofs. But again, I just want to warn everybody that this is just one of many different systems, and we're using it, again, because it makes for a nice sort of setup in terms of proof methods and a connection back to mathematics in later sections. So let's work on turning our previous informal proof into a formal proof in our Fitch system. And here's the proof that we had, that our argument that we were looking at in the blocks world was valid. And the only thing that we hadn't done was precisely justify the various rules. I think maybe the easiest one to justify now is the one where we substituted in B for D. So what we did in this step here, this intermediate step, is we took this premise, left of DE, and we took this premise here that B was identical to D, and we used that information to then replace that D with a B. And if you think for a moment, that's exactly what is entailed by equality elimination. So here we're using equality elimination. And again, anytime you use equality elimination, you need to cite some equality. So in this case, we're citing the fact that B is equal to D. And then we're substituting it into this statement up here. Everywhere we see that D, we're replacing it with a B. And we're making this conclusion left of BE. And you can always sort of check your step here as you go along, just to see if it's correct. In this case, you'll get a nice little check mark if you've correctly justified the sentence that you're looking at, or this intermediate consequence based on the previous steps. And notice here that you don't have to cite everything, only the relevant premises and intermediate conclusions that we had before. And these are these two here in red. Okay, so to access a different sentence, you click sort of on the left side of this bar. So let's now go up and talk about the justification for left of CB. Before, we were saying that the reason why we could assume left of CB is that left of was sort of this inverse relation of right of, right? So in the sort of the blocks world, if B is to the right of C, then C is to the left of B. Now, unfortunately, there's not going to be any introduction or elimination rules that allow us to infer something like that, because it's really information about sort of how these blocks are located on the grid. Now, fortunately, there is sort of a method still, and here I'm going to come down to this con. This is to stand for consequence, and I'm going to click on this top one called an, and this is short for analytic. So this is what we'll call an analytic consequence. And I'm going to click on that one, and then I'm also going to cite this sentence up here, because the conclusion we're trying to make is based on the fact that, okay, we know that this is true, so then we can sort of reverse those two and put left of instead of right of. Let me say a little bit about what ANCON is. It's not sort of an actual rule, but instead what it is a feature of this Fitch program. It has a built-in theorem prover. And what I mean by that is it sort of knows some basic facts about the blocks world and how the various predicates work. And then it has a automated system for proving facts about blocks. And when we type in something like left of CB, and we say, okay, assume right of BC, it takes that sort of thing that we've marked up here in red as an assumption, and it starts proving various things. And if at some point that system gets to a conclusion that left of CB is true, then it'll mark the statement is true. So let me go ahead and run that. So you can say check setup, and it gives me a little check mark, and it means that, yeah, indeed, based on sort of the basic assumptions of the blocks world, you can be assured that this statement is true. So again, that's called an analytic consequence. And anytime that you're proving something in the block world, it'll be helpful for things that are true about just sort of the nature of the blocks world. Okay, so we've justified this first intermediate consequence, the second intermediate consequence. Now let's finally justify this last step. And previously what we said is that it was a reflection of the fact that left of is a transitive relation, right? So if C is left of B and B is left of E, then we can say that C is left of E. And again, there's not really any introduction or elimination rules that are going to be helpful. The only two that we know are for equality, and equality is not really being sort of used here. Instead, we're using that transitivity. So again, what we would do is we ask ourselves, okay, maybe there's a rule that this Fitch system can come up with, or a proof, a basic proof that it can come up with that left of CE is true. But remember, if we don't sort of cite anything, it's going to say, no, there's not any proof, because you're not sort of making any assumptions. So here we'd have to say, okay, it's because C is left of B and B is left of E. And then let's look for some consequences of that in our proof sort of, or automated proof system that's available in Fitch here. And now if I check that sort of analytic consequence, it says, yeah, okay, there actually is one. And that's, again, based on the fact that, left of is transitive. And now we can go through and check the entire proof. And we see that now we've got check marks on each one of these. And so we have a nice formal proof in our Fitch style system of our original argument. And so we can be assured that it is certainly a valid statement. And again, notice that it's not anything about sort of the rigor of the statement or the rigor of the setup here. It's just more about the style between, the differences between a formal and an informal proof. So an informal proof, we just sort of stated what was going on, and the obvious consequences were sort of obvious. And the formalized proof, we're sort of writing everything out in detail and including it in this real nice stylized format. All right, so now that we've seen how to show a argument is valid using a formal proof, and how to analyze whether or not a valid argument is sound or unsound, we can say a bit about what we can do when we think an argument is invalid. And the way that we demonstrate that an argument is invalid is by constructing what we'll call a counterexample. So to find a counterexample, what you do is you construct a world or a description in which all of the premises are true, but the conclusion of the argument is false. And so one instance of this is enough to verify that the statement is invalid. So providing that example and constructing the details of why each one of the premises is true and the conclusion is false is the content of what we would mean by a counterexample.